Test. Okay, I guess you all can hear me. And can you see the slide? So, oh, seems today the delay is okay. Probably today delay take about 10 seconds, 5 to 10 seconds. I'll start the lecture at 12:30. Meanwhile, I just need to remind you that the assignment 2 deadline will be next 16 next week. Take notes the deadline. And yeah, a lot of students asking me whether they need to end the test or not. If you complete the assignment, of course, you can just simply end the test. And yeah, no harm to do so. If you not to do that, eventually in the end, I will do the end test to all the those unended cases. So at my end, I can do the end test for you if you didn't do that. So that is one thing you need to take notes. Second thing, I probably not able to return the code to you. So you better keep a copy for your own if you want to keep your answer. Yeah. So take notes on Git. Yeah, because we have 800 students, I can't everyone help you to download your code and then send back to you. And third thing for assignment 2, okay, I have repeat a few times in the lecture, but still a lot of students didn't watch the video and then keep asking me that about the prefix expression. The online one is probably not correct. If you yourself go and try it out and convert it back, you're trying to use the online one, all the online converter in those web, yeah, you will find that they only can let you convert to their prefix expression, but their prefix expression won't be able to convert it back to the original infix, implied that something is not correct. If you can do the conversion, definitely you can convert it to one expression and do the evaluation. Of course, these things should be able to let you return back to the original, convert it back to the original infix expression. If you can't do that, that means something is not correct. I have mentioned Git in the last lecture and highlight to you the thing that miss out is due to the left to right and right to left association problem. They forgot to consider that. They just blindly apply the postfix expression on the prefix expression conversion. In this week lab, you will go and try to implement it in the lab section. If you have doubt, you can clarify with your TA. I hope they can answer your doubt. If cannot, you can check with me. But try not to keep asking me that why online one is working, then they cannot use the same thing on the test cases. Yeah, because online one is not correct. Yeah, it's very simple. Yeah. So I think the right procedure is you after you watch a lecture, you attend the lab section, try out the lab section question first. If you can't, yeah, after that, then you can move to the assignment. That is the right procedure. But I think a lot of students skip all these steps, rushing for solving the assignment. Of course, you look harder. You should be step by step to do. And then if you find that there's any problem on the lab section, should trying to clarify it first. Yeah. So these are the things I'd like to highlight to you today before the lecture start. So today lecture I will cover another data structure called tree. Again, I still use the linked list, but just I construct the data structure in a non-linear way to build out a tree structure. And yeah, will the assignment end on automatic regardless of time left? Assignment 2, yes, it will be. I think normally I will end a few hour later lah. So you probably, some students still able to carry on after the deadline for a few hours. Yeah, but I will end it eventually, so have to take notes. Okay, so far I think you have learned about the dynamic memory management. Yeah, how to use the malloc and free. I think some student, yeah, you may need to take notes that when you declare some local variable in your function, you will find that I think I found some cases is they declare some local linked list, local variable static linked list instead of dynamic linked list. Then they work everything on that local variable. When you go back to your main function, you find that sometimes it works in your PC, but when you submit to the platform, it doesn't work. The reason is just because your PC didn't do the garbage correction after they finish in the local function. When they return back, suppose that particular linked list no longer exists, and just coincident that memory block still there, that then you in your main function you somehow still can access in your PC, but when you submit to the platform, it doesn't work because that actually not supposed to be there anymore. So it can be this kind of situation that your code is working in your PC, but it doesn't work in the platform. Actually, that implementation is not very correct. It just like certain system didn't do the garbage correction, the memory didn't clear your memory, and yeah, when they no longer need it, they just let it there temporarily. Then just nice that at that time you still can go back to that unclear portion to access the data, but actually those data should not be, it may not be there. If they do the system just like the platform, they clear the memory, then of course when you submit the code to the platform, it doesn't work because the memory already clear, no more such linked list there. So these are the things you need to take notes when you use the malloc free, when you use the local variable. What is the local variable means? You need to know. Yeah. So these are the things. Then this is the cell references the nodes we create for the linked list we have learned so far. In the linked list, we have used the print list, find nodes, insert nodes. These are the things I think you need to understand how to implement this function, how it works, and you yourself be able to implement them. But I think last time I also mentioned that you expect there are two types of question. One type is I give you a question, I give you a problem, and I will not provide you all this utility function. You need to solve the problem directly. That's one type. Another type is I provide you this utility function. You're trying to reuse them and solve the problem. Yeah, so during the test, you need to take notes that if it is the former case, that means I will not provide you this function in the template. Will you be able to rewrite all these things by your own? Yeah, that is a first problem. Yeah, you need to think about it. So make sure that without this function, you're also able to solve the problem by your own. Some question you find that I didn't provide you this function, although I allowed you to declare your own function, but you need to think about it. If during the test, will you be able to rewrite all these things by your own? If you can't properly, the better approach is directly solve the problem. That will be better. So And we also show you that, yeah, the difference between linked list and array. I think some students still trying to use the array. Well, you still also can solve the problem, but yeah, this module we tend to cover is about the linked list. Array, I just didn't create the very tricky test case. If I want to create the test cases which the array doesn't work, is possible. As long as I create a million data set in the test case, your array will fail because you may not have enough static memory for you to store such a big array. So these are the things you need to take notes. Of course, linked list is more flexible. The advantage to use the linked list is when your problem you need to during the runtime execution times, you need to insert and remove the data. And that circumstance, you need to use the linked list structure. And I think last week we covered some variation of the linked list, including doubly linked list, circular doubly linked list, and you name it. We also cover the stack and cube. So linked list typically is just insert the nodes. Yeah. So when we're talking about the stack or cube, it's just the idea is like stack is the last in first out. You see, it still function like a linked list, but under the stack data structure, you only allowed to push your data at the top and port your data at the top or at the front. And similarly to the queue, we additionally introduce a tail pointer because it's a first in first out. You only insert and queue your data at the back and dequeue it at the front. So that is the data structure still function like a linked list, just you add more additional constraint onto it to let it become a stack data structure or cube data structure. So of course, the data structure queue or stack, I can build it as a doubly linked list, circular doubly linked list is fine. But eventually, if when I call this particular data structure as a stack, which means I only can access the first item at the top, push it, port it, pick it, all this only work on the first item. So how it look like, whether it's a singly linked list or doubly linked list, it doesn't matter. I only do work with the first item only. So this is the stack and cube. And among all this, you will find that they are actually, we consider it as a linear data structure because they all work in linear, in one direction only. You only can insert the data. Yeah. So today we are going to cover is about the tree. Tree is a little bit different. Tree is not linear, it's a non-linear data structure. So what are the tree? So this is a typical tree data structure. Okay, it's a binary tree. So this tree have two children. Yeah, so this is the root. Then there's a two child, left child and right child, and then each of them always have a left child and right child. So it form a binary tree. Yeah, so you can consider tree is a special case of a graph, which we will cover in the second half. Yeah, but the difference between the tree and the graph is tree do not have this kind loop. Yeah, you can see graph, you can have this kind form. You can have a loop from here to here, and then you can back. But you find a tree, you cannot. For example, you want to you start from Anna. There's no way for you to go back to Anna again. So that means there's no cycle in this special graph. If I consider tree as a graph, yeah, tree does not have this cycle. You won't look back to to certain nodes. So that considered as a tree. Graph we will cover in the second half. Yeah, this is the typical graph. Because you can see this. If in this particular, if I clear this one, in this particular example, if I remove this edge, yeah, actually this one, I will consider it as a tree structure. It also is a tree. From 11, you have one, yeah. You have 2 children, yeah. Then this one also have 2. It may not be only any example. This one always only have 2 child. Yeah, if you look here, you will look at it. Actually, it's a tree. Yeah, sometimes only have 1 child. It also can be more than 2. Yeah, binary tree is only have 2, up to maximum you only can have 2 children. But generally, 3 can be, you can have any number. You can have more than 2 children. But later, also again have to take notes. In the latter example we will discuss is based on the binary tree. But actually, I can easily construct a 3 children tree. Yeah, this is still a tree. Yeah. But just you cannot have the common, that means you cannot have the common children. If this is the case, this is not a tree. Yeah, that means they have two nodes have the same child. This definitely not the correct one. Yeah, this is not considered as a tree already. If you have this kind of structure. Okay. So some terminology you need to know. So when we call, you will find different book, different problem. Yeah, we will name all these nodes. Some call nodes, some call vertex, some call like just now I use the child, or sometimes they also call leaf tree. Consider it as a tree, then they will call it as a leaf. Then all this is the edge. Then if you have a tree, so this is the root of a tree. And basically, if the nodes A, vertex A is the root of a tree, which means that A has no parent. So it considered is the root of a tree. Then and then A is the parent of B, C, D, E in this example. So B, C, D, E are sibling or children of A. Then if you, this part, you can consider it as a subtree. Under this E, so A can consider as a ascendant of the rest, not only B, C, D, E, F, G, H, all this is considered it as the ascendant. Then F, G, H, L, M is F, G, H, L, M considered as a descendants of B or A. Yeah, because A is the root. Then this particular one, we call it as a subtree of A. It's a subtree. Yeah. Then a subtree of H, for example, subtree of H is L and M. Yeah. All these are the subtree. It's in the big tree, you have some subtree inside. So, and then maybe clear the screen first. L and M has no children, so implied that L and M, F, G, L, M, C also, I, K, those in gray color nodes are leaf because they have no children. Then those B, H, D, E, J, these nodes called internal nodes. internal nodes because they have at least one child. For B have 3, 1, 2, 3. You have 3 children. For D, at least you have one. D have at least one child. In that case, B, H, D, J, E, these 5 nodes, we call it internal nodes. The rest in gray color is just a leaf. A is the root of this tree. So so another way they call this tree structure, they can consider it as a family. So like what I did, if A is the parent of B, C, D, E, B, C, D, E are siblings, and also they are the children of A. Okay. So these are just some names we will use usually. So a subtree of nodes B, this is the subtree. This is also a subtree. Even just one node is also considered is a subtree. Yeah. So this is also another subtree. Okay. So you can think the tree structure is there's a root, then they're trying to have a branch with a leaf. Yeah. Then they only have one root, and the root nodes have no parents. That's one thing you need to know. Yeah. So each node can easily branch out. That's why we call this thing is a nonlinear data structure. Yeah, they are not moved. Yeah, you can branch to form your data structure. Is not a linear structure. Yeah, you can easily branch out. But it should not merge up, because it should not merge. You only can branch out the some number of nodes. So, and then when we call the tree as a binary tree, each node has only up to 2 children. Up to. You can less than that, but only up to 2 children. So each node has only one parent. Yeah, the nodes pointing to it. So that is called binary tree. So general tree, of course, you can have as many links as you like. Depend your problem. So here got 3, here have 4. Yeah. Okay. So yeah, a tree basically is composed of several nodes. So just like I mentioned, yeah, B, H, D, E, J is considered as an internal nodes. Then the rest here, F, G, L, M, I, C, H, N, and K, these are leaf or external nodes, or you can call it external nodes. That's mean without children. These nodes has no children. Yeah, so it's considered as external nodes. Internal nodes is the one with at least one. You need to have at least one children. Yeah, root is the one has no parent. Whether you are internal nodes or external nodes, you will find that all of them have a parent. Yeah, this one has one, B. G has one parent, B. Then H has one parent, called B. Oh, this is the root. So why do you need a tree? Tree can, okay, very straight way is you want to build out your data, to build out their relationship, the hierarchical relationship between the item. Yeah. Then you can build, you can use the tree structure to build out your data in structure, have a tree structure to find out their relationship. That's one application. Why someone asking? I think the slide is already available in NTU Learn. You can download it by your own. So you can consider root as an internal nodes, but normally we call it as a root. Yeah. So yeah, when the application for having a tree, typical is like you build up a relationship, the hierarchical relationship. Like for example, maybe your personal structure, maybe the course you take different. There's a prerequisites. All this you can build up the tree structure. Yeah. So a lot of problem in your daily life you can to build out their relationship, then to let you to have a better picture, you can use the tree to construct and put the data into it. That's one way. Another one people use, we will cover later, like trying to more trying to compress the data. They're trying to based on their frequency to construct the relation, the how frequent you use certain word, then trying to do some coding. All this, we in the optimization problem we may use the tree structure, which we will discuss later, maybe next week. Another one I would like to talk about is some problem we don't really build the tree, like permutation. You find that you want to find out all the permutation cases when you playing some game. For example, I want to play this tic-tac-toe. I think probably you play before. Yeah, it's like trying to, you tick here, I cross here, then you tick here, I cross here, then you tick here, I cross here. Yeah, something like that. This can build a tree to analyze the possible combination. Yeah, you first step you can do this and this and this and this. You can do all these things. Yeah, so in each case I can, in this particular case, yeah, the next step you can do this and this and this and this and this. Your counter, the other second player can select this one. Yeah, these are all the possible cases. So through this, I can build up a tree structure and analyze all the possible scenario and decide what is the right strategy to win the game. Yeah, but this I have to highlight is like a lot of time we don't really build the whole tree structure. We just build when we visit the particular nodes, then we analyze it. Because to build this kind of structure, in this case is a 3x3. I think the combination is not that big. Still possible to build out the tree, but some game is too complicated that you can't build the whole tree structure before you analyze it. Yeah, so sometimes they may just build while they visit the nodes. Yeah, so they don't really physically build out the whole tree before they run the program. Yeah, like I said, when you encounter this kind of puzzle, another example, actually we will talk more details in the second half, is this very well-known 4 queens 8 queen puzzle. Original is, yeah, here I want to illustrate, I just simplify it to 4 queens. That means you want to put 4 queens in this 4x4 chessboard, and to ensure that no 2 queens can attach each other. So in that case, yeah, you can put the queen, the first queen here, or here, or here, or here. Yeah, these are all the possible case. Then next you can put it here. Of course, this is not the right way because you can attack each other. Yeah, based on this, you can build out a tree, which is the next queen you're going to place it. Of course, this one also not possible. This one also not possible. This one okay. Then based on this, you can carry on to put the third queen. This one okay. This one not okay. This one they can attack each other, not okay. This one you can attack each other, also not okay. then you can carry on to put the fourth queen. This one not okay. This one not okay. This one okay. So actually the answer is this. Yeah. So we can try to build out the tree to find out the answer. How to put 4 queen and ensure that no 2 queen can attack each other. So, but you will find that actually you don't really need to build the whole tree structure and find out all the pos. In fact, this one have more than one answer. Yeah, you have more than one solution. When you build out the whole tree, you will find out there are more than one solution, but you don't have to, because you can find that when you reach this point, you don't have to carry on to build to further analyze, because up to this point, this path is already not possible. It's not the possible solution. This one also not the possible solution. This also not the possible solution. Then no point to build the whole tree. Yeah, so when you encounter this kind of problem, although you are using the tree structure to solve the problem, but you don't really need to build the tree. This is another type. Yeah, we will cover this, how we solve this problem in the second half. Yeah, when we talk about the backtracking algorithm. Yeah, but here I just let you know that sometimes we are using the tree structure to solve the problem, but we don't really build the whole tree structure. This is another type of application of tree data structure. Yeah, so each node have 4 children. The height is only up to 5. So you only have, yeah, another word when we talk about the height of a tree, depend the book. So some is count the number of nodes. Here got the longest path I can have is from here to here to here to here. So 1, 2, 3, 4, 5. So here I can set the height of the tree is 5. But some book may call this is the height is 4, which they count the number of edges. So here have 1 edge, here have another edge, 2 edges, 3 edges, 4 edges. So therefore they call, some book may set the height of the tree is 4. This depends when you only have 1 node, what is the height of the tree? Some set 0, some set is 1. Depend the definition. There's no right or wrong. It's just the definition only. I define this, the height of this tree is 1. Then it start from 1. If I define the height of this tree, 1 node is a tree. Yeah. This is a tree. This is also a tree. Yeah. Okay, so tree also is a this one also can, yeah, all these are tree. Is here I show you the example is the binary tree. So this is a tree. So when they set the height of the tree, you need to take notes what is the definition. So especially the first nodes, when you only have 1 node, the height is 0 or 1. You start from 0 or start from 1. Then you may have different result. So this is something you need to take notes on the terminology. Okay, now back to how to create a tree. So actually you have learned about how to create a linked list, which you introduce a link. Then now for a binary tree, here I'm talking about binary tree, then I need 2 links. One for the left subtree. The other one is the link to the right subtree. So I just need 2 additional links instead of 1 in the linked list. So that is the basic binary tree nodes we need to have. Then once you have this, you can easily build out the 1 node and then link to the other 2 by the left pointer and right pointer. Then each node can link to its left pointer and right pointer. So these are some examples for a binary tree. Of course, you can easily extend it to a trinary tree or any arbitrary number of nodes. Depend. Probably, yeah, when you have more than 4, you will start trying to create an array. Or, yeah, the thing can be more and more complicated. So probably I will declare an array if the number of children is fixed. So I will probably, when the number of children is more than 3 or 4, I probably will declare a array pointer. That means here will become, instead of list now 4 pointer, I will use the array pointer to store all the link. Yeah. But for binary is only 2 is fine. Then I just declare left and right, easy to manage. Yeah. So if any nodes has no children or 1 child, then the others, so you will point to one of the link will point to the null pointer, just like this. That means when you encounter a null pointer, implied that this is the last node. Like this 94 example. The left child and right child all point to the null pointer, implied that 94 is a leaf which has no children. So you don't have to move. There's no way for you to move now further. Yeah, not really. I think someone mentioned it's the doubly linked list. Not exactly. Although doubly linked list, you also have 2 links. But this one, the 2, these 2 links point to 2 new nodes. And then doubly linked list, one of the link is point to the previous nodes. Yeah. So although the basic node structure look very similar, but the way you use these 2 pointer, you point to different memory block. You point to different nodes. End out that the structure will become very different. One is the doubly linked list. Doubly linked list is you have, each nodes have the 2 pointer, but one is point to the previous one. One point to the next one. This is a doubly linked list. Although they look very similar, but actually they are not exactly the same. But 3 are trying to, this one point to this one point to this one. And then this one will not point back to the one. You will point to another 2 new nodes. Okay, so this is the binary tree. Same thing, when you create such a tree, you should think about it. What can you use for it? How to use them? Yeah. So back to the utility function, display, search, insert, delete, sites. Yeah, you'll find that display, search, and sites, actually they are doing the same thing. In short, I'm trying to do the traversal. It's a traversal problem among the display, search, and site. That means I need to visit every node systematically. I want to display all the data, all the nodes, all the elements in this tree. That means I need to visit systematically every node in this particular tree. Search, I want to search whether something or at a certain location, whether have such thing or not. This kind of search problem is also a traversal problem. I need to visit every node, or I need to move in certain path to certain location to find whether such thing is there. So you need to systematically visit the nodes. Check the site is also the same thing. You want to know how many nodes are there. Of course, you need to do the count. You do the count, that means you need to systematically visit every node. So among these 5 functions, I will consider the display, search, and finding the sites are the same problem, traversal problem. So for linear data structure is quite easy. You just visit the first node, then go to the next node, go to the next node, and so on and so forth. But if you have a tree, how do you systematically visit all of them? Yeah, maybe sometimes it's here. Yeah, sometimes you only have one. Sometimes this one don't have, this one have. Yeah. How you systematically visit every node? Can a node in a tree point to a previous node in a tree? Well, theoretically, I can create such a tree to point the previous nodes to back is parent, but depend your problem. If you don't need to do so, you don't have to create that additional link. Yeah. Normally, when we build the tree, we only move in one direction. Unless there is the problem, you need to do so. Okay, how do we systematically visit all the nodes? There are a few ways. So here I'm going to introduce you two approach to visit all the nodes systematically. That's the key today you need to learn. So then you can at least solve this few problem. Yeah. To print all the content of a tree, search a nodes, or find the sites. Insert a nodes or remove a nodes. Actually, you also need to visit every nodes to find the target and then remove it. Yeah, this may be not only the traversal problem, but you will find that all these problem, usually first thing you need to know how to do it is how to visit every nodes systematically, so that you won't miss out any nodes in the tree, and you won't revisit the same nodes again and again. Yeah, so this traversal problem is something we usually discuss when we talk about tree and graph. Later, the same approach you will find that also can apply in the graph in the second half. So this is something important. So in short, you can break your problem into 3 sub-problems. So which means traversal problem, you can think that I'm trying to visit the root, and then I'm trying to visit should be the left subtree, and visit the right subtree. So you can think that your problem can become a 3 sub-problem. I need to visit the current nodes, which is a root, followed by the left subtree and right subtree. Yeah, the order not important. Later you will find that I have three versions. I also can visit the left subtree first, and then visit the left subtree first, and then visit the current nodes, and then the right subtree. As long as every time I repeatedly do this particular 3 step, eventually I can visit all the nodes, and I won't revisit the same nodes. Yeah, when you are in one of the subtree, you consider this is another tree. So in this subtree, the root is 31. Then also same thing, you're trying to visit the left subtree and right subtree. Then in this subtree, you also repeat the same procedure. You are trying to visit the root, followed by the left subtree and right subtree. So you will find that you are repeat the same procedure, and recursively. Every time you are trying to pass a subtree, a small tree, and then in this subtree, definitely there's a root. There's only one root, which is your current nodes, is the root. And then you're trying to visit it, and then followed by left subtree, right subtree, left subtree, right subtree. Eventually, you definitely will reach certain point which only have one node and no subtree. Yeah, then after you visit this particular nodes, you can return back already. So that will consider the base case. When only no nodes or one node, the tree with one node. Yeah, that will be the base case. Then after you do some process, you print something, you do some count, you increase your counter, or you display search. Search means that I'm trying to compare the content. You do some process, then you start return back. Then by doing this recursively, you will find that you will visit every node in the tree systematically. Maybe, yeah, you always visit the nodes, then trying to pass to visit the left subtree. This is another small tree, and then this one is another small tree. So it's like kind of like I would say this is a strategy like divide and conquer. I divide my problem into two sub problem. I myself is one small problem, and then and divide another two sub problem, and each sub problem are same as the big problem. It just the problem size becomes smaller, and then I trying to repeat the same procedure and solve it again and again and again. Eventually, I will solve the problem. So how to do this? This is the pseudo code. I visit the nodes first. So it's like here I call this is a pre-order that first traversal, because I visit the nodes, and then if the left subtree is available, I trying to pass the same function to visit the left subtree. And if the right subtree is available, after that I will try to visit the right subtree. So this traversal approach is known as pre-order depth first traversal. You'll find that this particular traversal, you can see from here in this diagram, you will move your travel as far as you can. You travel as far as you can, as depth as you can, and then after that you maybe you are trying to do some search. Maybe you're trying to print something. Maybe you are trying to do some counting. Yeah, but usually you'll find that this kind of depth first traversal is trying to travel as far as you can. Yeah, the leftmost subtree or rightmost subtree to search something or print something to visit the nodes, and then after that eventually you will return back to the root. So that is the depth first traversal. You start from the root of a tree, and then you're trying to explore as far as you can. And then after you done the job, you will start do the backtracking, return back. Yeah. So just now the one I show you, I visit first, and then I try to travel to the left subtree, right subtree. That is known as pre-order. You do the process first. So pre-order that first traversal. Of course, I can do the similar thing on in order. So pre-order, I process something on the current nodes, and then followed by visit the left subtree, visit the right subtree, repeat the same procedure. After I visit it, I try to travel to the left child, visit it first, then trying to visit the left subtree, then repeat the same procedure, then visit. Yeah. Visit it means that I trying to do some process. Depend on the problem. Maybe I increase the counter. Maybe I trying to do some comparison. Maybe I print it out. Just simply print it out, the output, the content. Yeah, depend what you want to do. Then after that, after I done the left side, I trying to work on the right side. Because no more subtree at A, then I will start return. When I return, yeah, so I will visit the right subtree. I'm trying to visit the right subtree. So just now I think someone asking whether I need to know the pointer point back to C. You find that in this case I don't really need, because my recursive function when I return, I will automatically go back to the earlier nodes. So because the recursive call, in other words, the recursive function, the stack memory help me to store where is the previous nodes. So I don't have to declare another pointer to point back to the parent. Yeah, because all this function, this traversal approach can help me to bring me back to my parent nodes, so I can visit the right subtree. So this is pre-order. Okay, so what is the in order depth first traversal? Is quite simple. You can see from here, you process, you visit the left subtree, right subtree. I just need to swap these two. Instead of process first, I visit the left subtree first. I visit the left subtree first. So in this case, I trying to swap these two steps. I visit the left subtree first and then process. I visit the left subtree and then process and then visit the right subtree. In this case, yeah, this one is clearer. I'm trying to move first. I'm trying to go to the leftmost subtree. Go to, if there's a left subtree available, I'm trying to move to the left subtree until I reach a point, a leaf nodes, probably is a leaf, may not, yeah, it may not be a leaf. It can have another one here. But as long as there's no more left subtree, I stop. Then I process. I do something on this particular nodes. And then I trying to visit, after that, I trying to visit the right subtree. In this case, okay, there's no right subtree. This is the one I just draw. Erase it. Yeah, no such thing. Then I will go back. Yeah, this B, all the left subtree already processed. The nodes you already processed. Then you will visit. So it's in order. You visit half of it, half of the subtree, and then you process the current nodes. And then you start trying to visit the right subtree. In this case, we call this is in order depth first traversal. Good question. Infix, postfix, prefix has nothing. They have some relationship. And I think you will be in the assignment. So I will release it soon. So you will find that later the algebra expression, you can build out an expression tree. To build out the expression tree, from the expression tree, you use the different order to visit it. You can print out different expression. Yeah, so that will be your assignment problem in the coming assignment. Yeah. So after I visit the left subtree, I process. Then I visit the right subtree. Then after I finish the right subtree, I will return. So I can easily find out my parent. I don't need any pointer to bring me, because this recursive function will help me to store where is my parent. So this one will go back. After he reached the E, all A, B, C, D, the right subtree already processed. Then I can visit the E. That's an in order depth first traversal. Then, of course, not surprising, what is the last one? The post order. Post order, which means you visit the left subtree, right subtree first. The post order, that's in post, you do the actual task after you visit the left and right. Okay, maybe this one quickly go through it. After you finish all of them, you will return back to the root. And then your job done for the in order. Next is the post order. You will find that you process in the end. Pre-order, you do it first. In order, you do it in the middle. Then post order is you do something after you visit the left and right. In that case, again, you also start from the root. You're trying to visit the left. You can move to the left, you're trying to move to the left. When you cannot move to the left, you will start trying to move to the right. When you cannot move to the left and the right subtree, that's in no more, like this case, then you will do the process. After you're done, you go B. You won't process the B. You will go to visit the C first, because there's a right subtree at B. So you are trying to go to C. C has, although C does not have the left subtree, it has a right subtree. You visit the right, then you start return. When C, all the subtree is visited, then you process. Then when B, all the subtree nodes is visited, then you will process the B. So that's the post order. You find that these three approach, they can help you to systematically visit the nodes in certain order, whether it's pre-order, in order, or post-order. So in this is so-called the post-order, because you will visit all the nodes at the left subtree as well as the right subtree. Then you process yourself, G. The left and right already processed. So you will process the current nodes, G. Then after you're done, you return back to its parent. The last nodes you do the process in the post order that first search definitely is the root. The root definitely is the last nodes you visit, you process, you do something on the root. That is the post order depth first traversal. Whether you choose which one, you will find that you always only visit each node once. Do the process once only. So this is the depth first traversal. Another one, you can depth first traversal. That means this one is trying to move as far as you can. Another approach is breadth first traversal. Breadth first traversal, you start from your tree, start from the root. Yeah, but you trying to visit the nodes level by level. Yeah, that means you're trying to process the closest nodes, all the closest nodes, all his children. After that, you visit all his grandchildren. This node, then these grandchildren. Then after you visit all the grandchildren, you visit all the grandchildren, and so on and so forth. Yeah, this is also systematically visit the nodes. We name it is breadth first traversal. Breadth first, the nearest one first. So in this case, you can see that every time I need to visit the nodes, I need to like queuing. Do you notice I'm queuing? I visit the level 1 first. From level 1, I will realize that there are two level 2 nodes available, 31 and 93. I need to put them in the queue and wait. I'm processing the node 70. So in the breakfast traversal level by level, I need to have a queue structure to help me to remember the order. Because after I visit 70, I need to visit 31 and 93. After I visit 31, then I will find out that after I visit 31, let's say it's a second node I visit, then I will find out that 31 has a child which is 14. This 14 will be visited after 93. After 93. So it is a queue structure. I need to queuing. All the nodes I revamp. Yeah, when I visit 93, I will revamp 73 and 94. These two nodes supposed to visit it after I visit 14. So it's in the queue. First in, first out. The first node you found will be the first node you process. First in, first out. So it's queuing. So to solve this breadth first traversal, level by level traversal, I need a queue data structure to help me to sort out the order. So in this case, you find that you expect you need to create a queue structure. And then first you enqueue the current nodes 70. And then you dequeue it. You dequeue it at the same time you check this 70 has whether it has a children. Before you dequeue, you need to check whether it has a children. You found that there's a two children, which is 31 and 93. So after you dequeue these 70 nodes, you will enqueue its children 31 and 93 in the queue. And then you dequeue one of them. You will repeat this process you after you encube them, you will decube 31 and encube is children 14. You will decube 93 and encube 73 and 94. You will decube 14 and cube 7 and 23. You will find that by doing so, I can visit the nodes level by level. Because the queue structure help me to sort out the order. The nearest one, the one with the lower level, I mean, if I name this root as a level 1, this one as a level 2, so you will find that all the in the queue, if you notice at any time instant, yeah, the low level one will always at the front. Like this one, like this moment, 93 will be always at the front. This is the level 1. Level 2 will be here. And this is level 2. 93 is in the level 2. Yeah, definitely the level 3 one will be at the back. Q will help me to sort out the order. Yeah, so that is the first in, first out data structure we use to help us to achieve this level by level traversal. So basically is encube, decube, encube, decube. You encube the current nodes and decube these nodes and encube its children if it is a variable. Yeah, so this is part of the implementation for breadth-first traversal. You expect initially, you start with the root, you encube the root, then you start run this while loop. Every time you just get the current nodes and then decube it, and trying to encube is the nodes, the left and the right. The left child and the right child enter the cube, and then we'll repeat this procedure. So eventually, you will visit the nodes level by level. So in short, you will find that depth-first search are using the recursive approach, and breadth-first traversal using a queue. So here is another example. Okay, before I move to another example. So depth-first search is a recursive function. I have mentioned earlier, recursive function, that means you are using a stack. Implicitly, you're using a stack data structure to sort out the visit nodes order. And level by level, breadth-first traversal are using the queue structure to queue the order, first in, first out. Then you will visit the nodes level by level. So these two are using different data structure to assist them to visit the nodes systematically. The depth-first traversal use the stack. Breadth-first traversal use the queue structure. Maybe the rest are the example. Maybe I will cover the example on Friday lecture. Maybe I can answer some question. How do we get back the B after visiting the A? Because you write it into a recursive form, you will find that when you do the recursive function call in the depth-first search, when you do for example, this example I will cover on Friday again. You'll find that every time you do this is a pre-order, you do the print job, we'll do the recursive call. When you call this function recursively, actually at the moment you call the recursive function, you are trying to put all the current state, that means the current pointer, the current nodes, the current memory location into a stack memory implicitly. The computer will do this job when you do the recursive function. Then when you go to the left subtree, you will do whatever visiting process there. When you return, the computer will pop up all the stack from the stack memory. So you don't really need to store. This process, when you do the recursive function, recursive call, the computer will do the job for you. Of course, you also can, that's in this particular function, if I want to, maybe I can put it in the lab section, in the lab question. Yeah, I think I will put it in the lab question. You can convert this particular recursive function into an iterative approach to implement this pre-order traversal in the iterative or non-recursive as a non-recursive function. In that case, you probably need a stack to help you. You need a stack memory to help you. Because when you visit the nodes, you can think about it. You have a nodes, you probably need a stack. You have to push the E into the stack. And then when you visit the B, when you visit the left subtree, you visit the B, you will push the B into the stack. That can be the memory address, the memory location where you store these particular nodes. When you push and then you visit the A, after that you find that A has no more children. Then you need to return. So what is the return? That means you need to pop up the nodes. When you pop up the nodes, you definitely go back to B first. When you pop up the nodes, you will find that you definitely will go to E. Yeah, the next one will be, after B will be E. Yeah, so that actually is a stack data structure. So actually, this kind of function is able to implement in non-recursive version. I will let you do it during the next week lab section. Anything I can answer? The lab schedule will depend on the group. The lab test, I will arrange and release it in the coming weeks. Yeah. So the stack is used for traversal. Yes. Pre-order, in-order, post-order. Yes. If you're not using the recursive, if you use the recursive version, you didn't see in this particular example, you can see that there's no stack. But it doesn't mean there's no stack. It's just like when you use a recursive function, implicitly the computer already use a stack data structure implicitly, so you don't need to declare. But if you want to convert this function to a non-recursive version, I expect you need a stack to help you to store the nodes. Yeah. So yes, it's a stack. If it's a breadth first traversal, then you use a queue. I mean, you implement the depth first without recursive and using a stack yourself. Yes, you need to explicitly declare a stack to store the parent nodes. So we have several lab instructor or TA in this course. You need to let me know your group, then I can tell you the person. Yeah, you can drop me an email. I can help you to find out their email address for you. Is the process in the traversal printing the item? Yeah, it can be anything. In this example here is printing. Of course, I can change this job to other things, other purpose, depend how you use the data. So this example is simple, it's just print out the result only. So you just print out. Yeah. Other things maybe they will do something. Yeah, depend. You want to compare, you want to do some calculation, you want to do. The key traversal is just to let you systematically visit every node. Ensure that you won't revisit the same node multiple times. Also ensure that you will visit every node. You won't miss out any one of them. That is the purpose to have a traversal algorithm. But what are you going to use it and print, count something, or do any evaluation is depend on the problem you have. Okay, if no further question, yeah, I still have a few slides to give you some example, which using the depth first search and breadth first search I will discuss on Friday, and probably I will include another slide about the binary search on Friday. Yeah. Okay. Thank you for attending today's lecture. Goodbye.